Assalamu alaikum. In today's lesson, we shall discuss about the differential equations. As you know that in real life situations, the quantities changes and we can measure their change. And by knowing the relation between different changes, we can come up with differential equations. For example, any expression, something like this is known as a differential equation. And let us discuss few examples. Say, for example, we have this differential equation dt over dt square. It describes the rate of change in temperature with respect to time, and it can be written as some constant and t minus tm. So it actually tells that the rate of change in temperature depends on the difference of the temperature between the object and the medium or the surrounding things. And similarly, there are many other quantities and phenomena. For example, this dn over dt is equal to minus lambda n. That is actually, it represents the population decay. For example, when we talk about a nuclear decay, um, in that situation, in radioactive decay situation, this model is helpful to understand the nuclear decay. Similarly, uh, an equation with this positive sign, for example, if there is some quantity, say q, divided by dt, and that quantity is changing, so we can put a positive sign over here. So with the negative sign, this is a decay model. With a positive sign, we can say that this is a population growth model, right? So first of all, let's in today's discussion, I'm only talking about how does a differential equation look like. Now, for example, let's start with a simple function. When we say that f y equal to f of x, so this is a function. For example, if this is x square plus 2 is a function. So this function look like this, horizontal line, and this is vertical, because this is x square plus 2. So we can say that this is simple x square and plus 2, it is somewhere over here like this, right? Or let us put it with the negative sign so that we can easily find out its root. So 2x square minus 2 is this equation, this graph. And when we solve this equation, so we can say that there is a point, this specific point, for example, over here when x is equal to 2. So at this point we can say that when we substitute 2 over here, so 2 square minus 2, that is also 2. So we can say that 2 is a point which exists on this curve. So a simple function, when we graph it, so we can have a line, a curve, any other shape. Now when we describe a differential equation, dy over dx equal to some function of x or y, or a combination of x and y. So differential dy over dx is actually tells us rate of change of one quantity with respect to the other quantity, or generally we can say that this is the gradient or slope at a specific point. So when we want to plot a differential equation, for example x-axis and y-axis, so we can say that this derivative or this gradient or the slope has a specific value at certain value of x and y. So for example, I'll show you some other example later on, but for the time being, let us say that if we have this equation dy over dx is equal to x plus y, uh, x plus y, like this. And so we can come up with the different values of dy over dx. Dy over dx can be positive 1, negative 1, positive 2, negative 2. It can have any value. Now for example, when we say that dy over dx is 1, so this is an equation x plus y. Now this equation represents a straight line. Now let's draw that straight line. X plus y equal to 1 can be written as x y is equal to minus x plus 1. So it would pass through this point like this, right? So this represents a straight line with a negative gradient, or let us write it, y is equal to minus x plus 1. Now this is a straight line which passes through y equal to 1 with the gradient minus 1. Over here derivative is 1. It means if we plot all the derivatives at all the points on this line, so these derivatives are 1. So over here the derivative is 1. Derivative is 1 means the gradient of at this point is equal to 1, right? So this straight line where all the gradients, all the slopes are exactly same, so this is known as isocline, right? So this is known as isocline. Iso means same, so same slope on this line. So similarly we can say that if if our slope is minus 1, let us say dy over dx is equal to minus 1, so we can write an equation like this: minus 1 equal to x plus y, and we can say that y is equal to minus x minus 1. In that case we can draw another line, for example this one, and it will pass through minus 1 with the same slope. And over here the slope is minus 1, right? Like this. Here everywhere the slope is minus 1. So similarly we can do this calculation for all the points on this x and y plane, and that is very tricky. Manually it is not we can do that, but now we have easily available different softwares, and we can use that software to draw the slope lines at all the points on this x and y field. Now this is known as the slope field. We can see that this is slope field, right? So a differential equation, for example a very simple differential equation, dy over dx equal to x, this is the slope field. These small slope element actually represent a slope field for dy over dx equal to x. Now because it is just a field, it does not give us an exact value, right? It can say that there could be a graph like this, means when we solve a differential equation we shall not get an exact value, but we shall get a field, and if we keep moving along the field, so we can come up with a solution that would be a function. When we solve a differential equation, so its solution would be a function, right? And if we know the initial condition, for example over here the initial condition x is equal to 2 and y is equal to 1, so we can substitute that point over here, and based on that we can draw a curve. If we have some other initial condition, for example if we have the initial condition which is 3 and minus 2, for example if the initial condition is 3 and minus 2, in that case our graph would be slightly different. For example it would be according to over here like this. We have to move according to these slope lines like this, right? So this way this would be our curve. So our solution would be different depending on the initial condition. Okay, now how do we solve it? How do we come up with this curve, or how do we find all these slope lines as we discussed above? we can simply plot the slope lines at different gradients. For example, we can choose dy over dx as, for example, minus 2, then minus 1, then at 0, then at x equal to 1, sorry, dy over dx equal to 1, then equal to 2. Then at every point, say at every point, we can get the value of x. Over here, according to this very simple equation, x equal to minus 2, this will remain minus 1, this will be 0, this is 1, and this is 2. So you can see that at x equal to minus 2, the gradient is minus 2. So I'm going to draw it over here. At x equal to minus 2, you can see that at this line, all the slope elements have the gradient minus 2. Similarly, at x equal to 0, so this is at x equal to 0, all the slope elements have gradient 0. And at x equal to 1, see, this is x equal to 1, all the slope elements, these small lines, have the gradient which is equal to 1. Okay, so when we plot all these slope lines, and we know some initial condition, so we can draw a curve. Similarly, another example, dy over dx equal to 1. So again, we can say that dy over dx can be minus 1, it can be 0, it can be positive 1, and based on this, we can say that over here y would be minus 1, 0, and 1. So it means that at y equal to minus 1, slope fields, these line segments will have a slope minus 1. So see, at y equal to minus 1, you can see that if I can change this density and the length, and as a result their position would be changed. Now you can see that at minus 1 their gradient are negative. At positive 1, see, at positive 1 their gradients are positive 1. Right? Similarly, at positive 2, see, at positive 2 the gradients are positive 2, and at negative 2, see, over here the gradients are negative 2. Okay, now if the initial condition is given, for example, initial condition is 2 2, so we can come up with this equation. But if the initial condition is, for example, 1 and minus 2, so our graph would be slightly different. Our graph would be like this. It would be like this. Okay, see, it would be a curve, it is continuously going down. So this is a way that that when we plot a differential equation, we get a slope field, and if we know some initial value, and based on initial value we can come up with certain function, right? We can come up with a certain graph and certain function. Now we can use some software. For example, I am using this GeoGebra, and it is very interesting and easy to use software. And for example, this is x plus 1, x plus y. We discussed this equation at the start. See, this is the curve, this is the solution. The solution tells us that when you solve it, you get a function. That function represents a graph, right? And how can we do that without doing the integration or anti-differentiation thing? Means that we can plot the slope field, and if we know the initial condition, then we can move along the slope field, and that that line will represent a function. That is the solution of our differential equation. I hope you understand all these things, and we can continue this topic in the next class, and we shall use the idea of this slope elements to solve a differential equation without doing some integration. Means there are some differential equations which are not easily solvable using analytical method or simple anti-differentiation or integration techniques. so we use a graphical or numerical method. So the idea of the slope field and at a different point, that will help us to solve a differential equation without doing the integration, and we shall discuss it in the next class. Okay, thank you.